This video is going to cover how to work the 6 steps of hypothesis testing for single sample t tests. This is from the Nolan and Heizen book, Statistics for the Behavioral Sciences, and this is specifically Dr. Buchanan's Psych 200 statistics course. So I have an example here where the sheriff is running for, or a candidate is running for sheriff who claims they're going to reduce the average speed of emergency response times. So we definitely already know that this is going to be a one-tailed test. The wanting to reduce them less than 30 minutes because 30 minutes is assumed to be the previous time. So that makes this mu. We don't have any records though, so we don't have the standard deviation, which means we don't have sigma. So sigma is a no-go, so we can't use a z-test. Thanks to this campaign, she's elected. Here are the scores. So we'll have to calculate the mean and standard error from those, and we're going to use 0.05. So we'll walk you through this, but know that I have already done the SPSS, and so if you would want to know how to actually run the test, go watch the single sample t-test video for running this in SPSS. This video is just going to cover how to work the 6 steps. So the first step is always to write down your assumptions. So that first assumption is that the DV is scale. Okay. And since we're talking about time here, the DV is scale. So it's a ratio scale because time is a ratio scale. Right. The second assumption is that we have randomly sampled or randomly selected. And with this particular data set, because we're talking about average response times, we do have access to all of the data. I know unless somebody didn't write it down, but we do have access to the entire data set, so we could randomly select 10 times to analyze. The last assumption is that is the data normal? Well, I don't know offhand, but the way to check that might be if n is greater than 30, but we don't meet that rule. So our DV is okay, our selection it could be true, but we do not have, we can't assume normality because I don't have at least 30 people. So part of step 2 and 1 is to list the sample and the population. So I'm going to list who's my sample over here, and who's the population over here. And I'm going to list the DV. So the sample is this new sheriff. We're comparing them to the old sheriff. And what are we comparing them on? Response times. So we have the new sheriff's times and the old sheriff's times, and we're comparing them on how fast they are. Okay, so don't be tempted, like I've said before, to put new sheriff versus response times, because then you're comparing the IV to the DV, but you need to compare the 2 levels of the IV on the DV instead. So I'm going to make this one my research, this one my null. So I'm going to rewrite my groups here. Okay, and we were expecting response times to go down. So I'm going to use a less than test, which makes this automatically greater than or equal to, so this is a one-tailed test for less than. Step 3, so like I said, I've already run this in SPSS, and this is the output I get. So I'm going to keep going. I wouldn't really rewrite this, but I wanted to show you how I kind of stack the data. So the sample is 10 people. That's this first one here is N. The mean is 28 minutes, so that's listed here under mean. Standard deviation is typically listed as SD or S, so 3.71. And standard error of the mean is 1.17. Now, note that they got this number from taking 3.71 or S over the square root of N. So it's the same formula as a z-test for standard error. It's just that now we're doing it over S over the square root of N instead of sigma. For the population, the only thing we have is mu, and that was 30 minutes from the example. So these are all the numbers we're going to work with. Now when you're running this, you want to make sure you enter mu. And so the top of the one sample test output here should say mu. If it says 0, if it says test value is 0 and mu is not 0, then you've done this wrong and your t-test score will be incorrect. But for step 4, what we really need is DF. So degrees of freedom is the number of scores that are free to vary and keep the same mean and standard deviation. So I have n minus 1 scores, and so if it's 10 minus 1, that makes our degrees of freedom 9, which is also listed here. So we're going to take the less than test, it's going to be 0.05, and we're going to use DF as 9 to determine what the cutoff score should be. So that makes it automatically negative. And I have a table right here. So I'm going to use this side for a one-tailed test, 0.05 this way, come all the way down to 9, so it's 1.833. So that makes us negative 1.833. Right, step 5 is where I actually calculate t. So I've got mean minus mu divided by standard error, which we had as 28 minus 30 over, the standard error is 1.17, I think. Yeah, 1.17. And that equals this number right here. So I got negative 1.70. So this is where I have my t found. I'm going to compare that to t critical here. So we decided, oops, wrong side. The cutoff score is negative 1.833. That's step 4. So everything out here to the left is reject. Everything over here to the right is fail to reject. Okay. And our score was a negative 1.70. That's step 5. So I'm going to fail to reject the null. So there might be a difference between the new sheriff's times and the old sheriff's times, but with these 10 times, I cannot reject the null. Okay. So when you reject the null, remember, you're not saying that the null is true, you're just saying I don't have any evidence to reject it. Okay. So with effect size, what I did was calculate this from MOTE. Okay. And you can get that at aggieerin.com or on Blackboard if you're in my course. And then there's a whole separate video on how to work MOTE with a link to download it. And I entered the sample mean, population mean, standard deviation, and at least n. But you'll see that it auto-calculates degrees of freedom and t for you, as well as standard error. Okay. But what we really want out of this is this number here. So for the effect size, D is equal to negative 0.54. That is a medium effect size. And how was that calculated? Well, we took D, mean minus mu, and then divided by S. So it's taking these two numbers and subtracting them, and then dividing by the sample standard deviation that I covered up, so 3.72. And that gave me a medium effect size. So there's probably a difference between the two, but at the moment I don't have enough evidence to support the research hypothesis. Now, for the confidence interval, what we want to do is take the sample mean plus m minus z critical. Okay, z cutoff, step 4 for a two-tailed test. That's the tricky part. And multiply that by standard error. So I'm going to have to back up a second because I'm going to take 28. Standard error out here is 1.17, 1.17. But I have to figure out what is z critical. Let's do the lower one here. Lower, upper. With a two-tailed test for 0.05 and 9 degrees of freedom. So let's go back to my t-chart here. Oop, too far. Okay. And now I'm going to use the same thing but a two-tailed test. Keep going here. 0.05, so 2.26. And we'll use a two-tailed test because most of the time confidence intervals are two-tailed. You can do a one-tailed confidence interval, but I think generally people want to know upper and lower for these sorts of things. So 262. let me calculate that really quick. So I've got 2.26 times 1.17. 28 minus that number, so I've got 2536 as my lower limit. I'm going to do the same thing. 2.26 times 1.17 plus 28, and I've got 30.64 as my upper limit. And so what that does for me is it tells me a range of scores that I would expect to find the true population mean. Okay, so if I do this again, 25 to 31-ish would be what I would expect. Now the way to check yourself is to make sure that the lower limit is actually below the number, so 25 is below 28, and the upper limit is above the number, 30 is above 28, and that they're roughly even. It's about 3 points on either side. Okay, so it shouldn't be 10 on one and 50 on another. Let's do one more example. So in this magic country, seniors report falling in love 2 times. We took 5 seniors, so here's N. Ooh, that looks funny. Let's try making that mu officially. There we go. And we asked them how many times, we took these 5 seniors and we transplanted them to the US. And we asked them how many times did they fall in love. And they gave us their numbers. So using 0.05, do students who go to a US country fall in love more often, so a greater than test, than people who stay in their own country? So first step is assumptions. Is the DV scale? And let's go yes, because I could fall in love no times, which makes it a ratio scale. Have we randomly selected? I can't really tell, but I'm pretty sure I probably don't have the access to the whole population for that one, because I wouldn't have like a database of all the students that are foreign, so probably not. Is the distribution normal? Well, I don't know, but N is definitely not greater than 30, so no. So we're not doing so good on this one. Yes, it's a good scale, no, and no. Okay. Step 2, I'm going to write down my sample, my population, oops, give myself some more space, population, and then what are the DV? The DV is falling in love. So how many times did you fall in love? Okay, give you a little heart there. So the sample is college singers who came to the U.S. versus people who stayed in their own country. Okay. And so I want to write the research and the null hypothesis. And I think the people who came to the U.S. fell in love more often than the people who didn't. So this is a one-tailed positive test. From SPSS, I have my sample statistics, where N is 5, the sample mean is 3.4, S is 1.52, and SM is 0.68. And my population numbers, where I know mu is 2.2. Okay. And so N, M, S, SM. And the next value, again, you want to make sure that this here is mu, or you have gotten the wrong numbers. But really here, I'm doing a one-tail p less than 0.05 test, and it's positive. It's a greater than test, so I know it needs to be positive over here. And we're going degrees of freedom, which is n minus 1, which is 4 in this example, which matches here. Okay. So what is that number? Well, I got my one-tailed test on this side, got 0.05. We're going to come down across here to 4, so it's 2.13. So our little car has to go 2.13 points to cross the finish line and reject the null. Remember that T is mean minus mu divided by SM. So 2.2, oops, wrong one. Back up. 3.4 minus 2.2 divided by 0.68, excuse me. So T found, last one's T critical, it's 1.77. So you can already tell this is going badly for us, because if we have a race car in the middle at 0, and we need to get to 2.13, because everything out here is reject the null. It's at the top because I picked a positive test. Everything down here is fail to reject the null. We only made it this far, and then our car died. So 1.77? Yeah. Okay, so we're trying to cross this finish line, and we didn't, so I would fail to reject. But we saw last time that if we calculate the effect size of this difference, that there's probably something there. It's a medium effect size, so let's see what happens this time. So again, I entered the sample mean, population mean, standard deviation, and N. It auto-calculated standard error for me. Huzzah. Look, I got the same T value. And look at Cohen's d this time. It's 0.79. That's a large effect size. So it appears there's probably a large difference between the means, but with only 5 students, I don't have enough power to find that difference. Remember, the formula for this is mean minus mu divided by S. So 3.4 minus 2.2 divided by 1.52. But be sure you enter the correct sample size when you enter things into MOTE, so that you get the rest of your numbers correct. Last but not least, let's do a confidence interval. So we've got 3.4 for the mean. And then we're going to add and subtract a T critical score times standard error. Okay, so minus and plus. But now I need to find a two-tailed T value for 4 degrees of freedom. Two-tailed over here, 0.05. Come across from 4, 2.776, because this is a two-sided confidence interval for 95%. 2.7, if we round up 8, 2.78. And then let's calculate those values. So we have 2.78 times 0.68 plus 3.4, or minus rather. So 1.51. And then 2.78 times 0.68 plus 3.4 all the way to 5.29. So think about this. The population mean is 2.2, and it is within the range of that interval, right? So 1.5 to 5.29 includes 2.2. So that is why we failed to reject. Okay. Especially we would have with a two-tailed test. But since we have a large effect size, I would say you would need more participants to be able to find a difference if there really is one there. And since the effect size is large, I would assume there's probably something there. So that is the 6 steps of hypothesis testing with effect sizes and confidence intervals for single sample t-tests.